All right, so welcome back, everybody. I had a doubt I asked in the class because it was pretty silent today. So I just want to get an overall feeling of how you feel, because I need to adapt to make sure. So who thinks I'm going too slow, just right, or too fast? To give you a bit of context, we are a bit ahead of time, so we really have time. If you have questions, I can take time to answer them and so on. So there is absolutely no time pressure. So I have the complete flexibility to make sure that that I'm aligned with you. Okay, so we have a majority of just right and a few people too fast. Okay, very good. So it's pretty balanced. Okay, so again, I am under no time pressure. So those of you who said too fast, if you have questions, I have more than enough time to answer them. So I can come back on anything you want me to come back on. This is absolutely no problem at all. Okay. So let me go back to, where is my, yep, to here, to the slides. To where we were. All right. So first, is there any questions in the lecture hall? Anything that wasn't clear? All clear? On Zoom, any questions? Anything you want me to re-explain? Nothing. All right. So I'm going to recap and show you how it's done in SQL. But again, to explain where we are. We have a language, SQL, that allows us to manipulate tables, right? And we can use select from where, group by, having, order by, limit of set, all of these instructions. Now, this is a language that is considered a declarative language and not an imperative language. A declarative language basically means that when you write a SQL query, you say what you want. You just declare what it is that you want out of the database. But in SQL, you are not instructing the computer to do it in this or that way. The computer is completely free to use any strategy it wants as long as the data that it gives you are correct, depending on your query. This has a name that's called data independence. Data independence is what gives us that freedom. And indices are the perfect example of an exploitation of that freedom. It means that if a user writes a query like select from where, and they are looking for a very specific record, like you have 8 million people in Switzerland and you're looking for a specific person with a social security number, for example, the query is the same. The query is just select star from population where a half our number equals such and such. But if you do it naively and you don't think too much about it, if you want to compute a query like that, you really have to scan through the entire data to find who has this AHAFO number. It can take a while to go through 8 million entries in Switzerland, right? And so this is why we cheat. We cheat, and PostgreSQL cheats by adding extra structures that allow you to accelerate that kind of queries. But it's in a way that the user doesn't notice. The only thing they're going to notice is that it's faster, but the results are the same. And what you have on your screen is exactly an example of that. Here you have the relational table that is the original data. Here you have the query, and this is the cheating part. The cheating part is this additional structure. In that case, it's a tree. It's organizing the values of a specific column as a tree. And we saw that when you have a tree like that, you can very quickly locate a value. It's just like looking a word in a dictionary, right? And that's what we saw is logarithmic time. Very quick, we locate a value and then we follow the pointers. So by using this structure, we are basically considerably faster than if we had directly tried to locate a record in the table. So this is the idea. And we looked at two kinds of structures. This is one. These are the B plus trees, or if you want, just say tree, a tree index. And then we have the hash indices, hash index, that is even faster, but that one doesn't support intervals. So the hash indices are very good at select from where with an equality. And the tree indices are very good with equality, greater than, smaller than, and so on. All of that, we can do it with trees. Okay. Now, a few more words about all of that. This is not free. This is not free, and there are two prices to pay. The first price that there is to pay is that you need some space in your memory to do that, and on disk. This actually consumes memory and disk space. So if you thought that you could just build an index on every column of every table and then that's it, everything is faster, think again, because you will not have enough memory and enough disk space to build an index for absolutely everything. You have to make a choice. You really have to decide what are the queries that I'm making, what are the most important columns that I want to index. You really have to think. So that's the first price. It's because you need space to actually hold that structure. You can see it in a book, right, that it takes space because you need maybe 10 or 20 pages at the end of the book for the alphabetical list of words. So it takes pages in a book. You need space for that. The second cost is time. It takes time because you saw when we built it, it took a few slides to actually build that. Now imagine building with a table that has a billion records in there. You have to build a tree. As you can imagine, you just don't snap your fingers. This is going to take several hours, maybe even several days to actually do that. So it also has a cost of actually building the index. So two things can happen typically in a database system. When you ask the system to build an index, you have two choices. The first choice is block everything, stop everything, build your index, you're completely unavailable, and I'm coming back in 2 days and the index is built. That's solution number one, right? So building the index stops the whole database system and you have to wait until it's done. Possibility number two is I'm continuing to use the database while it's building the index, but it's going to be slower during the time that it's actually building the index. It's like construction work. On the highway, you have one less lane. Right? So you have to just deal with a slower database while it's building the index. Now, this is when you build the index for an entire table. You already have the table, and then you say, okay, now I want this index. And then it's going to take 3 hours. But once you have built the index, it's not over. Because what happens then? You might insert records in the table. You might delete records from the table. You might update records from the table. And every single time you make an update to the table, inserting, deleting, or updating records, you also need to modify the index accordingly, right? If you insert a record, then you also need to insert it here. If you delete a record, you also need to delete it from here. If you update a value in a record, then you need to move it over to the new value, right? Who understands that? Right? So what it means concretely is that the moment you create an index, every time you write to the database, it's going to be slower to write to the database, right? Every single insert, delete, update is going to be slower. That's the price to pay for that, okay? So this is the general idea. Now, the next thing I would like to tell you is, how do you tell PostgreSQL to create these indices? We have commands for that. And it looks like this. So again, the context here is I have already created a table. I have already put data in there, right? There's maybe millions or billions of records in my table that's called publications. Maybe it's archive.org, right? It's the whole worldwide set of publications, scientific publications. There's millions, if not billions of them. And I want to create an index, a tree index on the column title. It's basically in order for people to search by title, and I want to very quickly locate that publication. Well, then I say create index. I give it whatever name I want. The name doesn't really matter. I called it by title, but I could have put anything in there. On publication, so that's the name of my table. And title, that's the name of the column that I want to index. So the values on that column are going to land in the leaves of the tree. Okay? And then you press enter, and this is when it gets lower, right? The moment you press enter, you have to basically wait until the system is going to build the index. And really keep in mind, it might take hours to actually do that. Okay? Once you have built that index, you come back a couple of hours later, the index is built, and then you can write a query like that. Now you could already write the query before, but before it was very slow. But if you come back after you have built the index, this now is going to be super fast. Logarithmic complexity. Okay? For whom does that make sense? Right? On Zoom, everybody following? Just making sure I'm leaving nobody behind. That was a good recap also for those who thought it was too fast. I don't see any raised hands in Zoom. Raise your hands if you understand. Okay. Some people following. Very good. So this is going to be then very fast. This other query is also going to be very fast. So now that you have the index, you can almost build your website and people can type the name of the publication and this is going to return very fast. In fact, this is the secret why when you connect to Amazon or you connect to Digitech Galaxus and you type the name of a product, this is very, very fast, right? Now we had a discussion in the break with you about other kinds of indices. For example, if you don't want to search for an exact title, but for example, you might want to search for specific keywords in a title, right? There's other kinds of indices for that. They're called full text indices, right? And then you can type keywords, and then if you look for products like a television or a phone and so on, then the system is going to be able to locate these words inside the values, right? By the way, I don't know if I already said it, but indices is the plural form of index. Some people say indexes, some people say indices. I tend to say indices, but it's just the plural form of index, indices. Okay. Here's another one where we created an index, but this time on the year column. So now if I would search for a specific year, that would be relatively fast. And if I'm looking for a year interval, then I can use the index, right? So now look at what's happening in here. I have a where clause that has multiple criteria. It's an AND, it's a combination. One of them turns out to be on a column that is indexed. The other one is on a column that is not indexed, because I'm assuming I have this one. This one is a different slide. I'm assuming I have this index only. Do you see now that I'm still able to use the index? I can use the index to accelerate that part. That will basically give me all the publications that are after 1905. It's a tree index, so it can do that. And then I need to do a bit of extra work. I need to look at all of those that I got from this, and I need to additionally apply that filter. So it means that that query might not be super fast, but it's a bit faster than it would have been without the index. Who understands that? Right? Very good. So now it's a bit of an extreme example, because now you're going to tell me the number of publications after 1905 is so gigantic that it will not help much, right? But this is really just an example, right? I could also say in the year between 1905 and 1906, for example, and then that would probably be much faster, because then it's a very small set. Okay. So this one is faster, but it requires a bit of extra work in order to also filter for these, because that is not in the index. Does this index help for that query? Absolutely not. The index here is totally useless. There's absolutely nothing we can do with it. That query is going to be slow, except if, of course, I would have built an index with title, right? But if the index on title doesn't exist, that query is slow. So what you need to have is really the intuition on whether an index helps make a specific query faster. And this is just thinking a little bit about it, right? But intuitively, it just means that the column must match. You must have a query that uses a column that is the same one that you index. Okay. This one is going to be faster because it's an interval. And as I said, if you use a tree index, then interval queries are going to be faster. Again, I repeat, it's a tree index. If you just say create index on publications, it's going to build a B+3, right? So it's a tree index. This one is another example of query that's going to be faster, right? You get the idea, right? So here is the part that is indexed, so that's going to be faster. And author Albert Einstein, I need to do additionally as post-filtering. It's called post-filtering. Now, what is interesting is that when I build a tree index, I can in fact also build a tree index on several columns. And then what happens is that it's called a lexicographic ordering. So in that case, what I'm doing is I'm indexing on years. And if the year is the same, then I differentiate by author. So I'm going to have basically, let's say, let me assume that the authors are letters like A, B, C. Then we are going to have, in that case, 2020A, 2020B, 2020C, 2020D in my B+3. Then I'm going to have 2021A, 2021B, 2021C, 2021D, and so on, right? So this is really first by year, then by author. You've all seen, I'm sure, these views on websites or even in a spreadsheet software. When you sort your data, you sort a table, and you have a first sorting criterion and then a second sorting criterion, right? You've all seen that. That's exactly what's going on here. We first sort by year, and for the same year, then we sort by author. So this is also going to give me a B+3 index. And then if I do a search by year and author, that's going to be very, very fast. Something else that I can tweak is I can tweak the order in which my index is going to handle that. And in fact, now you might think that's exactly the same thing that there is in the order by clause, right? In the order by clause, I can say ascending, descending, ask, desk, and so on. And in fact, it's logical because when you build an index, you are in fact sorting the values if it's a tree index, right? So this is exactly the reason why everything you have in the order by, you can also have in your create index. And that is going to make sure that your tree index is going to be sorting these values in the desired order. Okay. Now, maybe you don't want to tree index. Maybe you want a hash index. In that case, you just need to say it. If you add this using hash in the create index command, using hash, then it's going to create a hash index. Okay, that's the idea. So tree indices like this with just create index, and hash indices with create index using hash on a specific column. So here I'm repeating what I said. There is absolutely no free lunch. I basically said, yes, it's magic that you can do it on O of 1, but the magic has a price. So basically, if you don't have an index, then it will take time to answer the queries. But on the other hand, when you make updates against the table, it's fast to update the table. The moment you build an index, then some queries are going to become faster, but some updates are going to become slower. And again, that's because you need to update the index every time. So it's always a matter of compromise between the two. Okay. Who is with me? Very good. So now I have some example of the sort of things you can do in order to estimate whether it's worth having an index or not. So let's do a bit of some math. I hope I don't scare you too much with that. Let's see. Let's take the example of I have one table and I'm querying the table. Imagine it's a website, right? So people keep querying the table and people keep inserting stuff into the tables. We have queries that might use index 1, index 2, and so on, right? And then I'm asking the question, is it worth it to have these indices? Should I build index 1? Should I build index 2? And the sort of things you can do to estimate that is in terms of costs. So there's 4 possibilities. The first possibility is I choose not to have any index, nothing. Or I choose only to have index 1. that accelerates query 1, but not query 2. Or I choose to have index 2, that's going to accelerate query 2, but not query 1. Or I choose to have both indices, right? And then I try to estimate. So the idea, it's random numbers, right? But imagine the cost is for an insertion without an index, it's pretty low because you don't have any index to maintain, so inserting is fast. But Q1 and Q2, they take a lot of time, cost of 10. If you have index 1, then this is, as I told you, query 1 then suddenly becomes much faster, right? So lower cost. But inserting a value is going to take more time because you need to modify index 1 every time, right? If you choose index 2, it's the opposite. It's query 2 that's going to be faster. Query 1 is still going to be slow. And an insertion is also going to be slower than with no index at all. Then you probably guess the last one. If I have both indices, then my two queries are super fast. But my insertion now is even slower because now if I insert something into the table, I need to modify two indices. So it's much slower. And so now you might guess whether it's worth it or not depends on whether you have a lot of queries or a lot of inserts, right? Because if you keep inserting all the time, but you never query, then you shouldn't have an index, right? Because you're most of the time here. But imagine that you insert quite rarely ever into the table, and most of the time you just query, then of course that might be better, right? That's the intuition. But what is the threshold between the two? And one way to do that is to assume that imagine you have your website that is up and running with millions of visitors, and imagine that if you look at a lot of queries over time, then A is the percentage of query 1, it's a percent, so it's a number between 0 and 1. B is the percentage of Q2, query 2, and then the complement of what? So 100% minus A minus B is the percentage of updates. So basically, A, B, and the rest, 1 minus A and B. So basically, if you do the math here, then 2, that's the part that is here. So 2 times 1 minus A minus B, 10, that's with A, and 10 again for B. It's basically a weighted average, right? We're computing the weighted average of the costs, and the weights are the frequency in which they occur, right? So the more often a query occurs, the higher the weight I'm going to use. And so basically this is what I'm getting here, and I can just simplify it to this, and then I can fill the entire row in here. And now if I want to compare, I want to find out A and B in such a way that it's worth it. So imagine that I'm comparing these two here. I'm trying to estimate when is it worth having two indices rather than none at all. You just compare these two things, and basically it's worth it if the cost for the two indices is smaller than the cost for no index, right? So if this here is a larger number than this, then I should have my indices. And then if you simplify, you find it's if A and B, so the queries, if it's at least 1/3 of the time, if at least 1/3 of your queries in your website are actually reading queries, Q1 and Q2, and maybe the two remaining thirds might be insertions, then it's worth it, right? So that gives you the threshold. If it's at least 1/3 of the time that you have these queries, then you should have two indices. If, on the other hand, it's less than 1/3 of the time and you very rarely use Q1 and Q2, then you shouldn't have the indices. Okay? For whom does that make sense? Right? It's just an example of the sort of things that you can that you can do. Okay? In reality, it's not an easy decision. So typically, this is a problem that anybody who builds a website with a SQL database behind the website, they have to ask themselves, what indexes am I going to build? And you really have to consider the sort of queries that are run against your database. Now, you actually know the sort of queries that are run against your database, because where do these queries come from? They come from the business logic, right? The business logic, that's the Java code and the PHP codes that you have to run the website. And so you are in control of that if you control the website. So you just need to look at what the Java code or the PHP code is actually producing, the kind of SQL queries that they are producing, and then ask yourself what are the most frequent query patterns, and then you build your indexes based on these patterns that you expect, right? And then it should be in such a way that the website is smooth. It's when you visit it and type a search and so on, it should just be quick. So now you know the secrets of why it is, and when you go to Digitech Galaxus and type some products, then it's instant, and the page appears just like that, even though it's billions of products, right? So this is the actual, maybe millions, maybe not billions, but this is the secret behind how fast these websites are. Okay. So I'm done with indices. We are a bit ahead of time, as I said, so we are going to move over to data cubes. Before that, we are going to take some time for the course evaluation. Who has received the email? Okay, so I'm going to give you now 10 minutes to do it, so please do it now, also on Zoom, and I'm going to give you complete silence, and then I will start on data cubes just after that. So you just need to locate your email, open it, and answer.